Okay, so today we're going to discuss counting. And the first thing we're going to discuss is the fundamental counting rule. And what this says is that for a sequence of two events in which the first event can occur m ways and the second event can occur n ways, together the events can occur a total of m times n ways. So let's take a look at an example and how we're going to apply this fundamental counting rule. All right, so it says DNA nucleotides, and we're talking about DNA. DNA is made up of nucleotides. Each nucleotide can contain any of one of these nitrogenous bases, A, G, C, and T. All right? If one of these four bases must be selected three times to form a linear triple, so we're going to make triples out of these letters. We're going to use these four letters and we're going to form sequences of three letters. How many different triples are possible? Note that all four bases can be selected any note that all four can be selected for each of the three components of the triple. So what that means is, let's say we have a triple, right? We're going to choose three of those letters to form a triple. The first letter can be A. The second letter can also be A. So even if I select A, I'm going to replace A in the pool of things that can be selected, so I can actually select A again for the second letter in the triple. And let's say the last letter is G. So triples could be formed with letters repeated. So this is an example where these selections are being made or these events are occurring with replacement. So this fundamental counting rule can handle problems where you have replacement. All right. Now this distinguishes it. Oops. This distinguishes it from the other methods that we're going to, the other formulas that we're going to look at. Because in the other formulas, those formulas actually are explicitly for selections without replacement. But this is the principle that can handle selections made with replacement. It's more versatile than the others. This one can actually also be used if there's no replacement, but um, it's the only one that we're going to introduce that can be used when the selections are made with replacement. All right, so let's go ahead and use the fundamental counting rule to see how many ways we can make these three choices. All right, let's get rid of this. Okay, so the first choice, well, in making my first choice, the first choice, I can make a choice of any of these four different nucleotides. So I have any one of these four letters, A, G, C, or T, that can be selected for the first of the triple, the first letter of the triple. Now, the second letter of the triple, I can also select any of the four nucleotides. And to make the third selection is also of any of the four nucleotides. So each one of these selections can be made any of four ways. And what this rule says, well, if you extend this rule, that these first two decisions can be made 16 ways. So now I have the first two decisions already made. There's 16 ways of making the first two decisions. So now I've made my first two decisions and I have a number of ways that I can make that. And I'm going to see how many ways I can make the first two decisions and then make the third decision. Well, there are 16 ways of making the first two decisions, and then there are four ways of making the third decision. So in total, there are 64 ways of selecting one of these nucleotides for a triple. So that would be an example of using the fundamental counting rule. 64 ways that these bases can be selected to form a triple. All right, now the next one that we want to look at is the factorial rule, which is actually based on the fundamental counting rule. And Let's take a look at it. First, we want to look at the symbol, the factorial symbol, though. And the factorial symbol is this symbol. It's really just an exclamation point. Let's take a look at it now. The factorial symbol denotes the product of decreasing positive whole numbers. For example, 4 factorial is 4 times 3 times 2 times 1, which is 24. And this is just by definition. This really makes no sense if you think about it. By definition, 0 factorial is equal to 1. So this is just something you're going to have to remember. If you ever have a 0 factorial, it's really equal to the number 1. All right? Now here's how the factorial rule works. A collection of n different items can be arranged in order n factorial different ways. The factorial rule reflects the fact that the first item may be selected n ways, and the second item, because there's no replacement in this rule, the factorial rule, the second item can be selected in n minus 1 ways because we can't select the item that we selected first. So the factorial rule is basically when you apply the restriction of not replacing the object selected in the first trial to make your second selection. The factorial rule is what happens when you restrict the fundamental counting rule with that restriction that you can't, there's no replacement. All right. So the fundamental counting rule works with replacement. The factorial rule is the fundamental counting rule but without replacement. All right. So let's take a look and see an example of that. Okay, so here's the example in which we can use the factorial rule. Now, many newspapers carry jumble, a puzzle in which the reader must unscramble letters to form words. The letters B-U-J-O-M were included in the newspapers on the day this exercise was written. How many ways can the letters of B-U-J-O-M be arranged? I want to look at that part of the problem. How many ways can you arrange those letters? Well, let's see. Here there are 1, 2, 3, 4, 5 letters. So we have 5 letters. We have 5 things to choose from. And in this case, when we choose one of the letters, because it's jumble, we're not going to allow ourselves to choose that letter again. So this is indeed without replacement. We're not replacing the letters, so we're going to form a 5-letter word out of these letters, and we're not going to repeat any letters. So the first choice is out of 5 things. The second choice, well, in the second choice, you don't have whatever letter you chose first to choose from anymore, so there are only 4 choices. That's n minus 1, actually. N minus 1 is 4. And the third choice, of course, you only have 3 things to choose from, which is n minus 2, 5 minus 2. And the fourth choice, you only have 2 things to choose from, which is n minus 3. And the last choice, the fifth choice, well, the fifth choice, there's no longer any choice. There's only one thing left. It's n minus 4. And the fundamental counting rule says in order to find the probability of making all these choices, you'd multiply these things. But that actually equals to 5 factorial. And that's why I say that the factorial rule is really a special case of the fundamental counting principle. And you can see that because we used the fundamental counting principle, but it amounted to the factorial rule. So the answer to this, 5 times 4 times 3 times 2 times 1 is 120. So there are 120 different words that you can make with this. 120 is the solution. 120 different words that you can make with those letters. All right, the next rule I want to look at is the permutation rule. And the permutation rule, this is always used when it's without replacement. Notice right here, It says you have, one of the requirements is that this selection has to be made without replacement. We're selecting R of n total items. There are n different items available. N different items available. So these are the requirements for using this permutation rule. There have to be n things to choose from. We're not necessarily choosing all n of them, but we're choosing R out of the total n. So R cannot be a number bigger than n. Now, the distinction between this and the rule that we just learned, the factorial rule, is that in the factorial rule you have to be making selections of from n things, but you have to be selecting all n. So we're looking for the factorial rule. We're actually looking at the number of ways of rearranging the total n things, the factorial rule. So we're making a selection from the n different items, but we're making n selections in total. So the number of selections is equal to the number of items to select from. In this case, the number of items to select from can be a larger number than the number of items that we actually select. So we have those two numbers represented here as R, the number of items we actually select, and N, the number of items with which we have to select, or from which we have to select. So we have N different items, and we're selecting R of them. And the distinction between this and the next rule we're going to look at, is in the next rule we're going to look at, we're not going to have this 3 being the same requirement. The first two requirements are going to be the same for the next rule, which is the combination rule. You can take a look at down here. You see the first two requirements for both of these rules are exactly the same thing. The first two requirements. It's the third requirement that's different. So let's pay attention to this third requirement. It says, the third requirement is that we consider rearrangements of the same items to be different sequences. That means that the sequence ABC, and the sequence CBA are considered to be different even though they contain the same elements, the same letters. In this case down here, ABC and CBA would be considered to be the exact same thing. See, down here it says we consider rearrangements of the same items to be the same combination of things. ABC and CBA are the same when we're going to look at the combination rule. So the distinction between the permutation rule and the combination rule is, with the combination rule, the order in which we select the items does not matter. So ABC would constitute the same selection as CBA. And up here, the order does matter. So we use a permutation rule when the order does matter, and we use a combination rule when the order, sorry, I'm saying that backwards. We use the combination rule when the order does not matter, but this rule, the permutation rule, we use when the order does matter. See, the order matters because ABC and CBA are not the same sequence. All right, now here's a question that is kind of tricky because of what we call these things. We call them combination safes, but in reality, it's not the combination of numbers that you're trying to get. You're trying to get not only the correct numbers, but you're trying to get them in the correct order. So really, these safes should be called permutation safes, but they're called combination safes. But we're not going to be looking for a combination. We're going to use the permutation rule, and we understand that we're going to do that because the order in which we make the selections matter. Now, it says the author owns, this is the author Triola, the author owns a safe in which he stores all his great ideas for the next edition of this book. The safe combination consists of 4 numbers between 0 and 99. That's 100 numbers that we can select from. 0 to 99, 0 is the first number, 99 is the 100th number that we have to select from. If another author breaks in and tries to steal these ideas, what is the probability that he or she will get the correct combination, or actually permutation? Will get the correct permutation on the first attempt. Assume that the numbers are randomly selected. Give the number of possibilities. Does it seem feasible to try opening the safe by making random guesses for the combination? So now, this is what we're doing. We are taking 100 items we have to choose from. That is our value for n. we have the numbers from 0 to 100 to choose from, but we're not selecting all of those, right? We are selecting only three of them, I believe. No, four, sorry. We're selecting four of them. So R in this case, the number of items we're selecting out of the 100 is 4. And then what we're being asked to find here is the correct permutation of numbers that will give us the correct code to get into this combination safe. So, like, once again, it's a tricky wording because combination safe is actually it would be actually kind of a misnomer because it's actually a permutation of numbers that we're looking for. So what we're looking for is we're actually looking for 100. This is the notation. 100 is the first subscript, and then P, and then R. R is 4. So we're looking for 100 permutations, uh, 100p4. So the formula says that we're going to take n, which is 100, factorial, which is 100 times 99 times 98, all the way down to 1. And the denominator is going to be n, which is 100, minus r, which is 4 factorial, which, let's see, is 100 factorial over 96 factorial. And 100 factorial divided by 96 factorial is is equal to 9410 9400. Let's see, what's this? Ah, looks like 94 million ways, 94 million combinations or permutations, 94 different permutations that you would have to try theoretically to open the safe. So basically, if you were unlucky, I mean, you might get the safe open on the 94,109,400th try, which would take forever. All right, so the next rule we actually want to look at now is the combination rule. And like I said, the distinction between this rule and the last is that in this case, we're going to consider different sequences of the same three um, items to be the same. So ABC is no different than CBA. All right, so this rule says, all right, we still have the n different things, and we're selecting R of those n different things. And this is the formula here. And let's see, let's look at this example. It says, in phase 1 of a clinical trial with gene therapy used for treating HIV, 5 subjects were treated. Based on data from Medical News Today, if 20 people were eligible for the phase 1 treatment and a simple random sample of 5 is selected, how many different simple random samples are possible? What is the probability of each simple random sample? Well, let's see. We have 20 people to choose from, 20 people eligible for phase 1 of this treatment. 20 people, and of those 20 people, we are selecting 5. So R is equal to 5. And the first question asks us, how many different simple random samples, or how many different ways can we select these people? Now, in this case, the order in which we select the people for the sample doesn't matter. At the end of the day, if we select 5 people, it doesn't matter in which order those 5 people were selected. They all are a part of the same sample as they would be if they were selected in a different order. So in this case, the sequence does not matter. So ABC, Joe, Bob, and Jane would be the same as Jane, Bob, Joe. As long as it's the same 3 people, it's the same sample. Okay, and the second part of the question asks, what is the probability? Well, if we consider these to be equally likely, then if we consider the people to be equally likely of being to be selected, then well, it's going to be 1 over whatever number we get from the first part of this question to answer the second part of the question. So let's go ahead and do that. So what we're calculating is 20n C 5. So this would be read 20 choose 5. 20 ways, or sorry, 20 things to choose from. We want to select 5 of them. And how many ways are there of doing this? So this is going to equal 20 factorial over 20 minus 5. Oops. 20 factorial over 20 minus 5 factorial. And this is also going to be times 5 factorial. Because you see here, we have this extra factor in the denominator of r factorial. This is almost the permutation formula. If you take into consideration everything except what I have circled there in red, it's pretty much the same as the permutation formula, but we add this extra factor of r factorial in the denominator. So if we took away this 5 factorial, this would in fact be the permutation, the number of ways of permuting 5 things, permuting 20 things chosen 5 at a time. All right, so let's see what this is equal to is 15 factorial divided by, let's see, that would be 15 minus 20 would be, oops, 15, I'm thinking too far ahead here. It's not 15 factorial, it's 20 factorial, 20 factorial divided by 15 factorial goes here times 5 factorial. And let's see what that equals. So that's equal to 15,504. So there are 15,504 ways that we can make this selection. So, or we can select these 3 people or 5 people to be in this treatment program. So the probability of any one of these samples then, the second part of the question, the probability of selecting any one of these samples, the probability of, second part, what is the probability of each simple random sample? The probability of each random sample is 1 over that number, because there are that many and they're equally likely. So the probability of each random sample would be equal to 1 over 15,504.